Ionizing Radiation by Siley Blowers, Gregory Peterson, and Kate Way. Subtopics of this lesson: what is ionizing radiation? Hazards of exposure, units of exposure, tools for measurements, differences between alpha, beta, and gamma particles. What is ionizing radiation? Ionizing radiation is electromagnetic waves that carries enough energy to remove electrons from an atom. The two types of electromagnetic waves are gamma rays, which is produced by interaction within the nucleus, and X-rays that are produced outside the nucleus by electrons.
Three things happen when atoms from cells become ionized. 1, the cell dies. 2, the cell repairs itself. 3, cells mutate incorrectly and can cause cancer. Different cells can react to ionizing radiation, can react differently. Cells are most likely to be affected by ionizing radiation, which tend to be the one that reproduce cells and reproduce cells the fastest and are least specialized. Units of exposure to ionizing radiation. Electric charge freed by such radiation in a specified volume of air divided by the mass.
This is the radiation dose chart, as blues being the smallest. 1 blue particle is equivalent to sleeping next to someone, and then 400 blue particles is equivalent to 1 green particle, and 1 green particle is approximately equivalent to a chest x-ray, and 500 green particles is equivalent to 1 red particle, and 4 red particles is equivalent to what a radiation worker 1 year dose limit is, and 100 red particles is 1 yellow particle, which is 1 sievert. Tools for measurement. The first one is personal dosimeters, which are used by people in nuclear facilities and usually worn on their clothing. Second one is handheld detectors. Handheld detectors are used to measure the exposure rate from a specific object. And the third and final one is continuous sampling monitors, which can be set up to take samples of air and water in and around a low-level radioactive disposal facility and other places.
Difference between alpha, beta, and gamma particles. The alpha particles is composed of 2 protons and 2 neutron bonds together, or a helium nucleus. The beta particles are high in energy and speed emitted from radioactive material after decay. Gamma particles, similar to beta, get energy after decay, producing high energy and penetration by electromagnetic radiation.
By ionizing radiation, we mean radiation with sufficiently high energy to tear off electrons from atoms. Such radiation is emitted with the decay of radioactive nuclei, which may occur during nuclear reactions in the sun or in nuclear reactors. It can also be produced by various types of equipment used for diagnostic radiology and radiotherapy. The most common types of ionizing radiation is alpha, beta, and gamma radiation. Alpha radiation consists of positively charged helium nuclei. These are relatively large particles consisting of 2 protons and 2 neutrons, and because of their size and electrical charge, alpha radiation is quickly blocked when it hits matter. Even a sheet of paper or human skin is enough to stop alpha radiation completely. It travels no more than a few centimeters in air. Beta radiation, made up of electrons, have a lower mass than those particles that make up alpha radiation. Beta radiation generally has a much longer range, but glasses and thick clothing are enough to block it completely. Gamma rays and X-rays are electromagnetic radiation similar to radio waves and visible light, but with much shorter wavelength and thus higher energy. Gamma rays are produced by the rearrangement of particles in the atomic nuclei and X-rays, by the deceleration of charged particles or the transition of electrons in atoms. Gamma rays usually have higher energy than X-rays, and both have a much greater ability to penetrate matter than alpha and beta radiation. Gamma rays are only blocked to a minimal extent by the human body, and the speed only decreases insignificantly when traveling through air. A 5 to 10 centimeter sheet of lead or concrete layer of 50 to 75 centimeters would only reduce gamma radiation by 1,000th of its original value. The dominant contribution to the radiation doses which the general public is exposed to come from sources we have very little power to influence. Radiation in housing comes mainly from the radioactive substances in soil and building materials. Building materials and soil often contain radium, a product of the radioactive decay of uranium. With the decay of radium, radon gas is formed, which can penetrate into the housing. Each Swede is exposed to an average of 5 millisievert effective dose of radiation or radon gas. Each year, the majority, about 65%, comes from radon within the housing. Medical exposures, especially diagnostic radiology, account for nearly 15% of the annual radiation dose. The medical use of ionizing radiation is of great importance. Approximately every second Swede is examined using X-rays each year. Also, ionizing radiation is used in examinations and radiation therapy, primarily for the diagnostic and therapeutic purposes. All of us are continuously exposed to radiation, from both outer space as well as from radioactive substances in the bedrock. However, the dose of natural radiation depends on where you are. Different types of bedrock emit different doses. Also, people who live high above sea level may receive larger doses from outer space than those living closer to sea level. About 20% of the annual dose of radiation comes from these natural background sources of radiation. While we are not able to perceive ionizing radiation using our senses, it is easily measured with simple instruments and is even detectable using conventional photographic film. The Geiger-Miller apparatus is often used to detect ionizing radiation. The strength of the radiation is displayed on a scale, and a clattering sound indicates its intensity. Other ways of measuring radiation include TL, which is a dosimeter consisting of small tablets of a material that can remember the dose of radiation which it absorbs. During full-body scan, a person is placed in a room with thick, still walls, which block radiation from the outside and allow us to make measurements free from background radiation. When living tissue is exposed to radiation, cells can be injured or killed. The greater the radiation dose, the greater the damage to the tissue. If exposure is limited to a single organ, the damage will also be limited to that organ, and depending on the dose of radiation, the organ's function may be affected. If a certain dose of radiation is given over a longer period of time, the damage will generally be less than if the accumulated dose is given on a single occasion. Damage due to radiation is usually categorized as follows: specific lesions, e.g. small bowel injuries, pneumonia, underactive thyroid, foster injury, mental retardation, late damage, cancer, genetic damage. The damaging effect of exposure to low doses of radiation such as those we encounter on a daily basis, is still unclear. This is because symptoms or illnesses resulting of other than non-radiation-based causes overshadow the effects of radiation. The only known late damage that has been scientifically shown to result from radiation exposure is cancer. Hereditary, i.e., genetic damage, has not been demonstrated in humans. The activity of radioactive substance indicates the number of nuclei decaying per time unit. Activity is measured by becquerel, where 1 becquerel equals 1 decay per second. Radiation releases energy when it hits a human being. Absorbed dose is the amount of energy released into the human being per kilogram of body tissue, and is measured in the unit of gray. 1 gray equals 1 joule per kilogram. However, absorbed dose is not a clear measure of the harmfulness of radiation, because the various types of radiation affect tissue in different ways. To obtain a more precise measure, different types of radiation are given different weights by which the absorbed dose is multiplied. This way, doses that are more harmful and have greater weights result in a higher figure. This adjusted figure is expressed in the unit sievert, as 1 sievert represents an extremely large amount of absorbed dose. It is more common to speak in terms of millisieverts. The scale of radiation doses is one with a wide range. If we say that a lethal dose is 50 meters, the average Swede is exposed to a yearly radiation dose of a few centimeters, and the radiation we are subjected to during dental radiology would correspond to 1/100th of a centimeter. The lowest dose that has been associated to radiation-induced cancer corresponds to 50 centimeters.